Hi everyone, welcome to Simulation at the Speed of Design event. I am Hariharan Palaniswamy and I'm going to give a brief demo on Inspire Form. Inspire Form has three modules catering to specific design and simulation needs at different stages of the sheet metal product development. To start with, we have feasibility module that helps the product designers at the early design stage to improve the manufacturing feasibility of the design. You can quickly check the design for any potential defects like splits, wrinkles, and perform design iterations to improve upon them. Nesting analysis in feasibility helps to optimally lay out the flattened blanks to maximize the metal utilization and minimize metal cost. Once the design is released to manufacturing, die phase design module comes in and helps the manufacturing engineers to break down the steps or stages needed to make the part. Hybrid modeling environment inside Inspire Studio helps to quickly build multiple models for multiple die phase concepts. These die phase concepts can then be ideated with process simulation to improve upon them. Once the die phase designs are available, Inspire Form tryout comes in to prove those die phase concepts for any potential defects and improve the process robustness. Inspire Form tryout is like a virtual press where one can visualize the material flow at every step of the deformation and predict defects like wrinkles, splits, edge cracks, etc. during forming. And we can also predict spring back post forming. The die phases can then be compensated for spring back to improve the final part shape to meet the design fit and tolerance. Let's get into the Inspire Form demo. I will use an example part and I'm going to walk you through all the three modules to show how Inspire Form can help you with your day-to-day simulation needs and the best practice workflow to get the maximum benefit out of it. I'll be using this bracket for our demo today. We'll start with the feasibility module as a typical product designer. First, we prepare the model, then we do model setup, followed by analysis and results visualization. These functionalities are basically arranged in the same sequence going from left to right. Import model here is a thin solid, so we extract the metal surface to perform the feasibility analysis. Next, we identify and remove the features like flanges, holes, notches that will be formed in the secondary operation. In this model, we have a flange inside the hole, so we are going to first remove those flanges. Then we are going to fill all the holes. The goal here is to primarily prepare the model and make it as much close as possible to the shape that will be formed in the first forming operation. We can also open these flanges to predict the trim lines, and these trim lines are going to be very useful for us during the tryout simulation stage to trim the part, and also these trim lines can be useful during the die construction as well. Now the model preparation is complete, and we move on to the next step of setting up the model for the feasibility analysis. In the model setup stage, we'll start with assigning the material to the part. By default, Inspire Form comes with a metal database that is filled with SAE, European and Japanese metal standards. You can use the material available in our metal standard, or you can also create your own material and assign to the component as well. Next, we go to the Orient tool that helps to automatically establish the draw direction. These determined draw directions can also be modified by the user by selecting individual directions. You can also add boundary conditions like holding force, beats, etc. to mimic the real pressing conditions. In this case, we added a holding force all around the free edge of the part. This completes the model setup stage. Now we move to submitting the job for the analysis. In the analysis tab, you can specify the element size and you can choose whether to include spring back or not. The analysis usually takes few seconds. Once the analysis is complete, the results gets loaded in the same window. You can animate to see how the finished part is flattened to a flat blank. Feasibility analysis basically goes from finished part to flattened sheet. By default, we contour thinning results. It is a thickness change due to the forming process. Other results include formability, where the strains are plotted against the forming limit curve to predict failure. In case if there are any red dots, those indicates failure, and you can go ahead and use geometry functionalities inside Inspire Form and make changes to design and perform design iterations to improve upon them. You can also plot other results like strains, press tonnage needed to form the part, etc. Switching to spring back mode helps us to see what is the spring back deformation that likely you can see in the part post forming process. In addition to these results, we also export these results in other solver formats, and also the flattened blank is exported as an IGS file in the run directory as well. Blank fit and blank nesting analysis for metal utilization can be performed with the flattened blank. Here, the user can add extra metal or around, reflecting the addendum in the real die. Choose the type of stock between coil or a sheet, the type of manufacturing process, that could be either progressive or transfer die forming. Based on the manufacturing process, you can choose the type of fit or the type of carrier, and pick the layout to perform the nesting analysis. We also have overlap option that allows to study potential changes needed in the part design that can improve the metal utilization as well. Once the nesting run is complete, top 5 results that maximize the metal utilization for each layout is provided in this table. You can click on individual row on the table to visualize the results. You can also sort this table based on the column, so that way you can pick for a given particular layout what is the maximum utilization, etc. These nested layouts are also exported as IGS files in the run directory for downstream applications as well. Report allows us to publish a PowerPoint report with the model setup and the results information. This completes the typical feasibility analysis that a product designer would go through using Inspire form. Now we'll transfer this model to Inspire Studio with the Open in Studio option, and we'll start to create die phase concepts for detailed manufacturing analysis. In Inspire Studio die design, we start with the die phase creation by extracting the primary phase from the thin solid part. In this example, it will be the bottom phase. Next, we extract the free edges of the part that constitute the trim lines. At this stage, any cleanup needed on the free edges of the part can be performed. For example, we are going to clean up all these edge fillets on those flanges. Next, we break down the steps needed to form this part. It's recommended that we work backwards from the final part shape through the intermediate steps to the flattened blank. In this example, first we identify the flanges and the holes that will require a secondary operation. Then we go and identify all these walls on the edges that will also require another secondary operation as well. Then finally, we identify those waviness in the bottom of the part that will require a third secondary operation as well. All these identified features are listed in the browser as flanges, and you can select and hide them. This leaves us with the part shape that needs to be formed in the first operation, which usually is the forming or the draw operation. Now let's go ahead and create the draw die using this part shape as an input. We'll start with creating a flat binder, and we associate the free edges of the part to this flat binder. By default, the flat binder is created with dimensions, standard dimensions. You can always modify them. In this case, there is no addendum, so we're going to make the binder coincide with the part. And then we're going to combine the binder and the part using the draw die tool. This completes the draw die creation for the first forming operation. Now we move to the flange decoration for the second forming operation. Select the identified flanges that will be formed in this operation. We'll add a transfer of 100 mm to the second operation. And we're going to use the extend approach to create the flange die here. Select the free edges of the flange die input. It will basically create the extension of the surface to the bounding box using a straight line rib profile. You can adjust the size of the bounding box to adjust the size of the flange die. This completes the flange decoration for the second forming operation. Now we move to the flange decoration for the third forming operation. It follows a very similar workflow as the second operation. We pick the flange features to be formed in this stage, and we're going to define a transfer of 200 mm. And again, we're going to use the same extend approach to create the flange die. In this case, we are going to use a profile that is classified as start with a line. And this profile, we're going to add it at a given location of the part, and we're going to rotate the profile to point to the right box face, and that allows us to create this surface. This flange profile is made up of straight lines, arcs. These straight lines and arc dimensions can be parameterized, and you can modify them by clicking on the manipulator. This completes the flange die creation for the third operation. Operation 4 is trimming, where we'll punch the holes and slots. Now we move to flange die creation for the fifth operation. It again follows a very similar workflow as the previous operation. We pick the flange features to be formed in this stage and define a transfer of 300 mm. We're going to pick the part edge corresponding to which is basically inside the hole where the flange is attached. And we're going to create a flange surface, or the die surface for that matter, where we're going to deform the sheet in the opposite direction. So basically we start with the line rib approach, and then we rotated it to create this die face. This completes the flange recreation for the fifth operation. Now we move to the flange recreation for the sixth forming operation. It follows again the similar workflow as the previous one. We pick all the flange features to be formed in this operation, define a transfer of 400 millimeters. And again, we're going to use the extend approach, and we're going to start with the line rib profile to create the flange die. And we're going to pick the flange edges that is inside the hole, and we're going to create the die surface. Basically, that helps to deform the sheet to the final part shape. This completes the flange decoration for the sixth forming operation. Now the concept die face creation for all the forming operations are complete. That is basically going to deform the flat sheet into the finished part shape. Next, we transfer these die faces using export exchange option to the Inspire form for performing incremental analysis and virtually prove the design before manufacturing the physical tools. Inspire form tryout functionalities are arranged like in a physical process. We start with a blank definition, followed by a sequence of forming operation that can be added on fly. Like in real process, the blank gets deformed as it moves through this added process from left to right to get to the final part shape. Let's import the flat blank predicted from the feasibility analysis and select them as a blank in the tryout, and assign a thickness of 2 mm and assign the material from the material library. Add the single action draw as the first operation. Modify the draw direction to point along the die face normal. Select the draw die face that we created in Inspire Studio for the first operation as the bottom die in this case. We are selecting it as a bottom die because that bottom surface is our master when we created the die faces. Create the top die by offsetting the bottom die with the default values, and create a binder by copying the flat surface of the bottom die. The tools upon creation are automatically positioned in open position. You can also review the open and close position using the edit position options. You can also modify the open and tool positions by using manual approach in the edit options. The default process parameters are used for friction and holding for each of the tools. You can always modify them to the user specified value as well. This completes the single action draw setup for forming operation 1. Now add flange operation as the second forming operation. Select the blank and transfer it by 100 mm to locate it on the flange operation. Select the die face created in the die module as the bottom die for the flange tool. Create the top die by offsetting the bottom die with the default offset values. And then we're going to remove the top pad and add bottom pad from the repository. And for the bottom pad, we're going to copy the surface that corresponds to the feature formed in the operation 1. And once the tools are created, they are automatically positioned. You can go to edit position here and manually modify the tool position. In this case, we are giving a stroke of 18 mm to the bottom pad and manually positioning it with a stroke of 18 mm for the open position. This completes the operation 2, which is the flange operation. The workflow setup for the third forming operation is again similar to the previous one. Add a flange operation as the third operation here. The blank is again transferred by another 100 mm to the third operation position. Select the third die face that we created in Studio for the bottom die, and again create the top die by offsetting the bottom die with the default offset values. And we are going to add the bottom pad from the repository, remove the top pad, and we're going to select the features that are formed in operation 1 and operation 2 as the surfaces for the bottom pad. Again, we are going to locate the bottom pad above the bottom die with a stroke of 18 mm using the edit position options. This completes the model setup for operation 3, which is the flange operation. Add trim as the fourth operation, and the trimming stage, we are going to transfer the blank by another 100 mm. Select the trim lines that corresponds to the hole and the developed trim lines from the feasibility analysis for trimming those notches or slots. The trim directions for each of those trim lines are automatically calculated and shown as a blue arrow. You can always double click on those arrows and modify the trim directions as well. This completes the operation for trim die setup. Now add flange operation as the fifth operation. The model setup here is very similar to the operation 2 and 3. In this case, the trimming and flanging is happening in the same location, so there is no blank transfer involved. Again, we're going to select the die face that was created using die model for the bottom die, and we're going to offset by the default offset thickness or offset value to create the top die. In this case, we are going to create the top pad where we're going to copy the surface of the bottom die corresponding to the features found in stage 1 and 2 and 3 to create the top pad. Again, we can use the edit position and locate the top pad if needed as well. This completes the setup for operation 5, which is the flanging operation. Add flange as the sixth operation, and again transfer the blank by another 100 millimeter. In this case, we're going to select the die face that we created as a bottom die, and we're going to offset the bottom die to create the top die using the default thickness value. Now we're going to remove the bottom pad and add 2 cam dies because we need cam tools to basically form these flanges. These flanges need to be formed in a different direction compared to the forming direction or the draw direction. To create the flange dies, select the surface corresponding to those flanges. And these cam dies are going to basically move in a different direction from the forming direction. So in this case, it's going to be moving x-axis on this side. And on the right side, the same flanges are formed, but the cam die is going to move at the negative x-axis. Once the tools are created, they are automatically positioned in open position. This completes the operation 6 flange setup. Now we have pretty much completed the model setup for all the operations that we initially envisioned during the die face creation. Click on Run to submit the job for the analysis. The job can be either submitted in your local laptop or in a compute cluster within your enterprise, or you can submit it to a remote cloud as well. In the Analysis tab, you can specify the element size and data for the analysis. Once the job is submitted, you can track the progress of the run using the Run Status dialog that's visible on the screen. Also, you can visualize the results live by clicking on the View Now button at any time during the run. Once the run is complete, you can click on the green flag to load the results. You can animate to see how the sheet is deforming from the flat blank to the finished part through all the stages. As you can see, the blank is getting transferred at the end of every operation to the next operation, carrying the stress and strain history, and then completing all the forming operations like in the real press. By default, we contour thinning results. It is a thickness change due to the forming process. You can also contour FLC, for example. In case of forming limit curve, we basically plot the strains against the forming limit curve and check for any failures. Red dots indicates failures. In case of failures, you can go ahead and modify the die geometry, either inside Inspire or Inspire Studio, that has a lot of geometry functionalities to make quick changes, and perform simulations and improve upon them with multiple iterations. Other results that can be plotted include major and minor curvature. That helps us an idea about the bending radius at different locations in the form part. The dominant deformation mode helps us to see whether bending or stretching is dominant while deforming the part into the finished part shape. Edge strain helps us to predict any potential opportunities for edge cracking. And skid marks lets us know whether there is going to be a scratch between the tool and the part during the forming process, and where likely any skid marks that you can see it on the finished part. We can also plot tool forces to get an idea about what is the tonnage needed to make this part as well. Here I showed you simply the results for the sixth or the final forming operation. You can similarly look at individual forming operation results as well. Report publishes the PowerPoint report that includes model setup and the results for all the forming stages. And redesign can help to optimize blank shape trim lines for net shape manufacturing. Here we started with a blank shape from feasibility analysis. The form part doesn't exactly match with the design part, as you can see. Now by selecting the edges of the design part, Inspire Form can back calculate and come with the optimal blank shape that when formed will match exactly with the formed shape. The predicted blank shape is what we see in red. This is just one example of how simulation can help us in estimating the unknowns. The same can be extended, for example, to figure out what should be the drawbeats needed or the blank holding force needed to make the part. In summary, in this demo, we went through a typical workflow, how Inspire Form can help with the design and decision-making process at the various stages of sheet metal product development. This is what we have for you today within the short time frame. I know there's a lot of information. I went through it very quickly. I hope I covered what you're looking for and you enjoyed it. I hope you will start using Inspire Form for all your stamping simulation needs. Thank you very much for your time and thank you for joining Simulation at the Speed of Design event. See you next time.